Hello, everyone. We are starting chapter 7, and we get to talk about bonding, more details about covalent bonding, and then you guys actually get to start building molecules. Later on, we will actually look at molecules in 3D space, and you'll be able to predict their geometries. Okay, the first thing we need to do is just look at what really a covalent bond is. You guys already know that it's involving shared electrons. The electron of one atom is attracted to the positive nucleus of the other. And so let me just show you a really basic energy model for the hydrogen atom. So each of these gray balls represents a hydrogen atom. Let's start actually on this right side here. This is an energy diagram, which you're now becoming more familiar with, where energy is increasing as you go up. And this is more potential energy. You want to think about it as balls on a spring. The higher the energy, maybe they're too close together, they're going to just spring apart. So that's potential energy. When the atoms are too far apart, they're just not interacting. So if you think about a hydrogen atom, it has one electron, there's nothing really going on. But as they get closer together, one of the electrons of one guy is attracted to the nucleus of the other guy, and they end up forming a bond where each of their electrons are shared between them. There's a perfect distance where you're minimizing repulsion of nuclei and electrons, and you're maximizing that plus minus electrostatic attraction. It gives us this bond length of hydrogen at 74 picometers. If you try to push them too close together, though, it's like forcing two like charges together, and they're just going to get too high in energy and want to spring apart. So that's shown here. So this is a very classic well energy diagram showing the well here for this lowering of energy when you form a covalent bond. So overall, just remember, you could start at a neutral energy, but when you form a covalent bond, you release energy. That's why you have this well, this energy line going down. And the reason you release energy, plus attracts minus. Okay, a little bit of some language. We talk about bond order, which is basically the number of bonds and between two atoms. So if you have a CC single bond, the bond order is 1. A double bond shown by 2 lines is a bond order of 2, and then 3 for a triple bond. It's specifically the number of electron pairs between the atoms. So what we'll see later is for compounds that the electrons can actually move across the molecule, you can actually have electrons spread out through a molecule, and sometimes you can actually have a 1.5 bond order. One thing I really need you guys to know, and just leave this course, go into your next chemistry course or biochem course, is that when you break bonds, that requires energy. That's an endothermic process always. So here's a little cartoon in HH bond. It takes this big muscly guy energy to break it apart. The reason is the plus and minus attraction between proton and electron is very, very strong. That's why stuff exists. Matter would not exist at all if we did not have this attraction. So to break that apart, to separate proton Penelope from her beloved electron Ed, you gotta supply energy. You guys have already seen this, but I wanna remind you, in an energy diagram, this is glucose burning to give carbon dioxide and water. Any chemical reaction will have some sort of hill. Sometimes they're really high hills to climb to go to the product. So again, on the left is reactants, on the right is products. Sometimes the hill is low. You don't need much energy. Those are favorable reactions that'll go almost spontaneously. Whatever the reaction though, you have some sort of hill to climb. It's because you have to break the bonds of the reactants. You have to destroy the reactants because you need to break those bonds to reform those bonds and release energy to give some sort of product. This particular diagram here is exothermic because the products are actually lower in energy. So overall, you release more than you had to put in. But sometimes you have endothermic where the products are way up here. But either way, you have an upward hill part of the energy diagram, and that's because energy needs to be added, and energy is increasing as you go up. Okay, let me help you connect bond strength with bond length. So if we look at a carbon-oxygen bond, you can have a single, double, or triple bond. The more bonds you have, the stronger the hold is between them. The greater the attraction, they're actually pulled in more. Think about 3 chains holding 2 objects together versus 1 chain. It'll be harder to break 3 chains. So basically, the shorter the bond, the stronger the bond. The more bonds you have, the shorter it gets. I can show you data for that to convince you. Here's the bond length as we go from single to double to triple. It does get shorter. These are in picometers. And I could show you data of the bond energy. As you go from single to double to triple, the bond energy increasingly gets higher. So again, in this case, a triple bond is the strongest, then a double bond, then a single bond. And the connection is the triple bond has a shorter bond, so the shorter the bond, the stronger the bond. It's just harder to break them apart. They're closer together. Plus and minus are closer together. Another trend you need to know, and this is based off of what you learned in chapter 6, is that number 1, as you go down the periodic table, atomic radii increases. Hopefully you remember why. It's because as you add more electrons, you're going into greater n levels, and those are further and further out from the nucleus. So what if I now start forming bonds with those? So let's just look down the halogens. An F alone is smaller than a Cl, Br, and I is the biggest out of the halogens. But now what happens when I start forming bonds? So if I make those diatomic molecules, look at this. The bonds will be shorter if the radii is shorter. The bond length, will be shorter here because fluorine's smaller. Iodine's bigger, so it'll have a longer length. This is really important for you to know. It's like, think of iodine as 2 big beach balls. The centers are going to be further apart than if you had 2 little ping pong balls. Like in fluorine, that would be closer together. You do see that reflected in experimental data showing fluorine. It has a shorter bond length than iodine. So again, if I ask you questions about bond length, you have to go back to what you learned about atomic radii and which one's bigger and smaller, and know the trends. One way to remember the trend is cesium, the lower left, is the biggest, and fluorine towards the right and up, it gets smaller. So I have it here as well. And we can use this to look at going across the periodic table. You guys know that size decreases. The reason is the number of protons increase. So it constricts the electrons closer to the nucleus. So now what if I hold one atom constant? Like say I have a carbon atom and I bond it to an N, or I take carbon bonded to an O, or carbon bonded to an F. So I'm progressively going to the right. I'm taking carbon, which doesn't change. It's always carbon, but I bond with something increasingly smaller. So the radii get smaller, so your bond length gets smaller. And as you make a shorter bond, your bond energies increase. So again, shorter bond, stronger bond, but here the length has to do with what size radii you're talking about. The one thing I want to warn you about is some people think the further apart things are on the periodic table, the longer the length. That has nothing to do with it. It just has to do with what you're comparing and the trend. So don't think like, oh, if I'm way over here and here, that's going to be longer than something here and here. I mean, it's not necessarily true. Something really useful that you can get out of bond energies is the enthalpy of reaction. So if you think back to chapter 9, the thermochemistry chapter, Basically, every reaction can have an energy associated with it. As it proceeds, it could be endo or exothermic, and there's a number attached to that as it proceeds, as the reaction's written. So at the core of that is the energy it takes to break bonds of the reactants and the energy released when you form bonds. So again, it always takes energy to break bonds, and energy is always released when you form bonds. That's why you're going to see we have a negative sign in our equation to calculate this. You can calculate enthalpy of reaction, delta AHxn, by just taking the sum of all the bonds broken minus the sum of all the bonds formed. So be very careful. You do have to pay attention to how many bonds are broken. So sometimes I might give you a picture of a molecule and you might have to count how many bonds are in there and how many of those molecules. So here I'm forming two HFs. I'm breaking an H bond and a fluorine bond and forming two HF bonds. If I use this equation and these given energies, let me just show you how to do this. If you want, you could pause and try it. So I just take the energies of the bonds broken, and the ones broken are the reactants, because you got to break and supply energy to break the bonds. So for one HH, 432 here, and one fluorine, 159, and then it's minus the sum of all the bonds formed. So minus 2 times 565. 2 because I formed two HFs, which have a bond energy of 565. Crunch those numbers, you get minus 539 kilojoules. What that tells you is that if this reaction proceeds with 1 mole of hydrogen, 1 mole of F2, forming 2 moles of HF, the delta H, it's exothermic and releases 539 kilojoules. We're going to move into talking about electronegativity and polarity of molecules. And I need to introduce Linus Pauling because he's just an amazing chemist. I was actually in college when he died, so I remember this really clear because I was learning about all of his contributions to science. And I won't tell you the whole story, but you can look up his story. He really came from a disadvantaged background. His mom said not to go to college. There was no value in a college education. He ended up pursuing science in Oregon, and then ended up at Caltech, won a Nobel Prize in chemistry and won the Nobel Peace Prize. The chemistry work was for work in quantum mechanics. He actually did a fellowship with Niels Bohr and Erwin Schrödinger. And then he made the contribution of the alpha helix model that you're probably familiar with, and he developed the electronegativity scale. His Nobel Peace Prize was actually work for him voicing his position against using nuclear bombs. So if you're familiar with the Manhattan Project, that was a project gathering the world's genius chemists, physicists, chemical engineers to make the atomic bomb that ended up bombing Japan during World War II. And he was invited and he declined. He said, that is against my values. And he wrote this huge manifesto and was a huge pacifist and really voiced his opinion not to use those sort of weapons of mass destruction. So he ends up developing the electronegativity scale, which is really critical for understanding polarity of molecules, but also that really tells us a lot about whether or not molecules are going to react or how they'll react. If you end up in organic chemistry, this is huge for predicting chemical reactivity. So electronegativity is basically a property of an atom. And it's the tendency of an atom to attract electrons. So the most electronegative are on this upper right corner of the periodic table. Fluorine is the most electronegative. There are numbers associated with this. Fluorine gets a 4. Cesium is the least down here. It's a 0.7. You can kind of see that it loosely tracks with size. The closer an atom can get to the closer an electron can get to an atom's nucleus, the more it's held. So you'll see that kind of trend here. N, O, or F, including chlorine, those are some of the most electronegative. What we're going to see is, depending on atoms paired, the greater the electronegativity, they're more on the ionic side or polar side. Very little difference in electronegativity, we call that nonpolar. So when you actually have a bond, electrons shared between atoms, it's not always perfectly shared. So you can have an H and an H. Those have identical electronegativities. And so that is perfectly shared. We call that nonpolar covalent. If a difference in electronegativity is less than 0.5, like HH or Cl2, we call that nonpolar, but it's still a covalent bond. If it's something in between 0.5 and 2, it's polar covalent. So that would be like HCl. Greater than 2, that's really extreme. That's between a metal and a non-metal, for example, and that ends up being ionic. So much so that electrons are transferred. So let me go back. So things between metals here it depends. This isn't always black and white, but definitely if you could get a difference greater than 2, paired with other guys here, you're definitely in the ionic range. Most of the bonds that we'll talk about in the covalent realm will be polar covalent unless there's a really similar electronegativity. So look at this region here. These all have really similar electronegativities. The differences won't be greater than 0.5. These end up being nonpolar. So even though sulfur and carbon are far apart on the periodic table here, or there's some spaces in between, they have identical electronegativity. So that just a CS bond would be nonpolar. Look at hydrogen. It's way over here, but it has an electronegativity of 2.1. So just remember, H slips in between boron and carbon. That's why all the hydrocarbons, HC bonds, these are found in a lot of organic compounds, those are nonpolar. There is no polarity associated. Those that are polar, we show a dipole. This is a vector pointing towards the more negative end, which we give a partial negative sign. So this is a Greek symbol delta, but that means partial. So these aren't real negative or positive charges like cation and anion. These are part, meaning the electrons here are perfectly centered. They're shifted more towards chlorine. And we show that with this dipole, where the barbed end is a plus sign to show that that's a more positive end, and it goes towards the more negative end. These are called dipole moments that have an actual magnitude. So there is a number associated with these, and there's a direction. This comes into play when we start looking at overall 3D shapes of molecules. And what you can actually find is, even if there are bond dipoles, if they're all perfectly evenly spaced out, opposing each other, then they can actually cancel out, and you can have an overall net dipole moment where there is no polarity to the molecule. This is going to be really good for you guys to see for your upcoming lab. Basically, this is an electrostatic potential map, and it helps us visualize with color the more negative and positive ends. So HF, I said, was polar. Towards the fluorine here on the right, it's more red. Red is more negative, blue is more positive. For HH, this is nonpolar covalent, so there is no blue or red end. There is no plus or minus end. For sodium chloride ionic, it's more pronounced. So you guys will be seeing, using Spartan student, negative and positive ends, and blue is partial positive, red is partial negative. Something really cool is, if you just look at bond energies, HH is 430 kilojoules per mole, OO is 180. But if you look up the bond energy for OH, it's actually higher than either of those. And that's a little surprising. That was surprising to scientists, because they thought, oh, maybe it'd be something in between. Why would it be higher? Have a think, pause this, and have a think why the OH bond would be stronger. What is special about the OH bond versus these others? And we just talked about polarity. There is polarity, right? Near the O is a partial negative end, near the H is a partial positive end. So the reason why it's stronger is you do have this part positive, part negative, part of this bond that have an attraction. So there's this added electrostatic attraction component to this. This is something that maybe you just thought of, you just figured out yourself. This is something that Linus Pauling came up with as well. Okay, the last little bit that we're going to talk about is drawing electron dot or Lewis dot structures. Lewis for the guy that developed electron dot. This is important for predicting whether molecules can exist. It can predict the polarity, solubility, forces between molecules, and indicate 3D shape. So this is a really important part of chemistry, and going forward, something you'll use in your next few chemistry or biochem courses. The basis for this is the number of outer or valence electrons. We've already gone through electron configuration, but each group has its own outer or valence electron number. So for example, group 4 has 4, and we space these around the 4 sides of the atom. So it has 4 unpaired electrons. It'll want to make 4 bonds. Hydrogen only has 1 unpaired, so it'll only make 1 bond. Group 5, when you put the 5 electrons around, and the max you can have is 2 on each side. We call that a lone pair or non-bonding pair. You can see that group 5, nitrogen, phosphorus, arsenic, if we keep going, has 3 unpaired electrons, so it wants to form 3 bonds. Go to oxygen's group 6, sulfur, selenium, 2 unpaired electrons, it wants to form 2 bonds. So the halides will form 1 bond, and then the inert gases, noble gases, those already have a full octet, so that's why they're primarily inert. So all of these want to form 8 electrons around them or complete what's called an octet. Hydrogen only can have a max of 2, we call it a duet, and it's always a terminal or end atom for a molecule because it can only form 1 bond. Group 3, which I don't put on here, but it's boron and aluminum, they have 3 outer electrons and they're special. They can actually just pair those 3 to get a max of 6, and they're happy with 6. They're the only ones that are happy with 6, or they could also keep going and have 8. So they're okay with 3 or 4 bonds. I mentioned a non-bonding or lone pair electrons. This is a type of an electron pair. The other type of electron pair is a bonding electron pair here. So a single bond means you have 2 electrons. You could draw them out if you want, or it could be represented with a line. So hydrogen likes to form 1 bond. Oxygen likes to have 2 lone pairs and 2 bonds. So they form water in this manner. I'm going to show you in this last little bit how to draw Lewis dot structures, and this is just for simple molecules. In our next video, we'll talk a little bit more in detail about other types of molecules. The first thing is put the least electronegative atom in the center. So the one to the left or lower on the periodic table. Hydrogen will always be on the end though. You'll use the group number of the atom to decide how many more bonds it needs to make its octet. Remember, each bond equals 2 electrons. And then you're going to connect the atoms so that the octets are filled. Keeping in mind, group 3 can have 3 bonds or 4 if it wants to. So I'm going to go over 3 examples. The first is a chlorofluorocarbon, CCl2F2. That means you have a carbon, identify that it has 4 unpaired electrons, 2 chlorines with 7 outer electrons, so it only has 1 unpaired, and 2, I thought this was H2, I apologize, I'm going to change this to H2, but 2 H's here. So the way this will bond is carbon needs to make 4 bonds. That's perfect because you have 4 different atoms that want to make 1 bond. So you just arrange them around carbon. Carbon is sharing its 1 electron, or each of its 4 electrons to each of them. Notice I put 2 chlorines here. You could have had chlorine across, chlorine up here. It doesn't matter. That's not specified, so don't worry about that. And then another way to visualize this or write it is just instead of the 2 electrons in between the atoms, you could put a single bond for each of those to simplify it. Later on, when we just look at shapes, you don't even need to put these outer ones. But right now, you still need to, if I ask you for an electron dot structure, you need to show all of the electrons. And for me, you can put just the single bonds for the interior ones. For NH3, if you had to draw the electron dot structure, you would start by writing the electron dot for N. It has a lone pair and 3 bonds. Sorry, 3 unpaired electrons to make 3 bonds, and then 3 H's that want to make 1 bond. So naturally, you would make 3 bonds to H, and you still have this unpaired, non-bonded lone pair here. So that's your answer. If you wanted, you could have, instead of the line, you could have put 2 dots for a bond. The last one is carbon dioxide. Carbon, 4 unpaired electrons. Oxygen has 2 lone pairs and 2 unpaired electrons, and there are 2 of them. So what's interesting is carbon wants 4 bonds, but there aren't 4 atoms. So here you could start thinking about multiple bonds, double bonds or triple bonds. And so one way to rearrange the electrons is, instead of oxygen forming 2 single bonds, it can use 2 electrons, and carbon can use 2 electrons, and they can form a double bond. You could do that to both sides. So since 2 electrons is a bond, you can show that structure written this way as well. You may have played around with drawing this, paused it and played around with drawing this, and you could have come up with another structure with a valid structure that obeys the octet rule, uses the correct number of valence electrons. You could have come up with this structure here. Both of these are possible. So there are times when you could draw multiple structures that seem to be right, and they might be right. They probably are correct, but I will tell you that usually you can determine if there's a preferred one or not preferred one. In this case, both of these are valid. However, this is preferred. I know it's preferred because oxygen in general prefers 2 lone pairs and 2 bonds. Here you have oxygen with 3 lone pairs and a bond, or 3 bonds and 1 lone pair. So both are correct. Eventually what we'll learn is this is preferred. These are actually what are called resonance structures, and they can both make a contribution to the overall structure, but the major contributor to the structure is this one. Okay, that is where I'm going to end here, and next time we will talk a little bit more about these resonance structures, draw a little bit more advanced electron dot structures, and then also talk about geometry and molecules in 3D space.